All right, guys, it's time for fun with math. And so today we're going to talk about something called Taylor polynomial. So real quick, what is a Taylor polynomial? Well, the idea is if you have a function, so here I have the function 1 divided by 1 minus x, you can actually create a polynomial to approximate that function. And so down here, I have what are called the Taylor polynomials centered at 0. And so this is the 0 Taylor polynomial. And then this is the first polynomial. And what you want to notice is over here, there's the graph of my function. And as you increase the degree of the Taylor polynomial, so the second Taylor polynomial has degree 2, it looks a little bit more like the function. The third degree Taylor polynomial, of course, has degree 3. It looks a little bit more, and so on and so forth. And by the time you get to the 7th degree Taylor polynomial, the two functions look almost identical to each other, especially if you focus what's happening at x equals 0. So down here at x equals 0, you have a point. The graph around those points are almost identical from looking at them. And so that's basically what we're going to do today. Today, we're going to learn how to create these Taylor polynomials given a function. And so here is the definition of a Taylor polynomial. So the kth degree Taylor polynomial, f of x, centered at a. So if you give me a function, I can create this polynomial. And so here we have t sub k of x, so the kth degree Taylor polynomial, the k Taylor polynomial. And notice it's just using the value of the function and the at where it's centered and its derivatives, right? So you have a second derivative here, the third derivative, and then all the way up to the kth derivative, and then you stop. So here's the big idea. So the big idea is if you have a function, so here's my x and y axis. And so here's my function. Let's just call this function f of x. And you give me a point A, there's going to be a point on the function here. And so the height of that function, of course, is f of a. And so at that point, there's lots of information from the function. So what kind of information is at that point? Well, you have the height. So I'm just going to kind of make a list of things here. So you have the height, f of a. The function has a derivative of a, so you have f prime of a, which gives you the rate of change of that function. You have the second derivative, which gives you the concavity for that function. And then we can just continue on. So you have the third derivative of that function evaluated at a, and so on and so forth, dot, dot, dot. And that can go on forever and ever. And so if we stop it, though, if we stop it at the kth derivative, so the kth derivative f evaluated at a, then we can use this information right here. So we can use this information and we can build this polynomial. And it turns out that this polynomial gives a pretty good approximation for the function at that point. Right? Now, outside that point, it may get a little bit chaotic in some sense, in the sense of not actually looking like the function, but around it here, so kind of around it, it looks almost like that a function, especially as k gets bigger and bigger. So in the next lecture, we'll talk about Taylor series, which is then we let just k go to infinity. And so then you get basically sort of like the best polynomial type approximation. It's not really a polynomial, it's a power series. But that's the big idea, okay? So let's just do a couple of these problems. And so here, we're going to find the kth degree Taylor polynomial centered at 0, approximating the given function. So we're going back and looking at this function we looked at the very beginning here, f of x equals 1 divided by 1 minus x. And so what do we want to do? So let's kind of take this slow. We want to find the 4th degree Taylor polynomial. So we're going to write this down. So you have t sub 4 of x. And what is that equal to? Well, it's equal to, and it's centered at 0. So you have f of 0 plus f prime of 0 divided by 1 factorial, and then have x to the 1 plus f double prime of 0 divided by 2 factorial. and then times x squared, and then plus, and this pattern just keeps continuing. So the third derivative evaluated at 0, and then divide by 3 factorial, and then times x cubed. And then finally, this is a fourth degree polynomial, so we'll stop here. And so here I have the fourth derivative of f evaluated at 0 divided by 4 factorial times x to the fourth. So what's my job? My job here is then to go and find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, or the third derivative of f, and then the fourth derivative of f, and then I can stop. And I'm hoping then I'll see a pattern so I don't have to continue doing this for the 6th degree and 8th degree Taylor polynomials. And you'll see actually a pattern does develop. So to do this somewhat systematically, how are we going to do it? Well, let's just make a table. So over here, I'll make a table. And so what will be in my table? So I'll have n in my table. I'll have the nth derivative of the function in my table. And so let me make this better. So nth derivative, we put little parentheses up here around the n. So it's the nth, that stands for the nth derivative of my function. And then I'm also, kind of a big space here. Then I'll also plug in 0. So I'll have the nth derivative of the function, and move over a little bit, and then evaluate it at 0. So there's my table. And I'm going to zoom out just a little bit. There we go. Okay. So I'm going to do this for what values of n? Well, I'll do it first for n is equal to 0. So the 0th derivative is just the function. So the function is just equal to, and for my function here, guys, f of x is equal to 1 over 1 minus x. I'm going to use, because I have to take a derivative, I'm going to use 1 minus x to the negative 1. When I take the derivative. So right here, this is just 1 minus x to the negative 1. And then when n is 1, I take my first derivative. So what's going to happen? So we'll go a little bit slow here. So the negative 1's going to pop down. So I'm going to get negative 1 minus x to the negative 2. And then times the derivative of the inside, which is another negative 1. The derivative of the inside, the derivative of 1 is just 0. And then minus x is a minus 1. So you just get negative 1 on the outside here. And so notice the negatives are going to cancel. So this is going to equal what? 1 minus x to the negative 2. And then we'll do it again. So now I'll do it for 2. And so I take a derivative again. It's a second derivative. So I take this and take a derivative of that. So the negative 2 is going to pop down. So negative 2 times 1 minus x. And I take away 1 from that. So negative 3. And then times a negative 1 again. That's the derivative of the inside. And again, notice what's going to happen is the negatives are going to cancel. So I get 2 times 1 minus x to the negative 3. And we're just going to keep on going until we get to 4. So keep on going. Let me extend this down a little bit. And so the next one would be the third derivative. So I look at this guy here. The negative 3 is going to go down, but I'm going to drop off the negative because I kind of see what's going to happen here. So I'm going to get 3 times 2 times 1 minus x to the negative 4. And notice times negative 1, but that's going to cancel that negative in front there. So I'm just going to drop it off. And then the fourth derivative, negative 4, is going to come down. So I'm going to get 4 times 3 times 2. Now it is negative, but again, when I take derivative of the inside, that negative is going to drop off. So negative to negative 5, and then derivative of the inside is negative, so that negative is going to drop off. And that's all I needed. And so then I'm going to plug in 0 for all my x's. So when you plug in 0 right here, you're just going to get 1. When you plug 0 in right here, you're going to get 1 again. When you plug 0 in right here, you're going to get 2. All right, so you just put a 0 right there, you get 2. And then down here, you get a 0, you get 3 times 2. And if you put a 0 right here, you get 4 times 3 times 2. And you know what? I think if this was 5, I would get 5 times 4 times 3 times 2 times 1, basically, which is 5 factorial. So there is a pattern developing here. But now I can find this fourth degree Taylor polynomial simply by plugging in what I found for these derivatives. So let's do this. So what's f of 0? Well, f of 0 is equal to 1. So I have 1 plus what's f prime of 0? Well, I come over here. It's also equal to 1. So 1 divided by this 1 factorial times x. And then plus, what's f double prime is 0? Well, this is 2, which is really the same thing as 2 factorial. So if you want, I'll put 2 factorial over 2 factorial x squared. And in fact, here I could put a 1 factorial. You're going to see that these are just going to cancel in the end. And then the third derivative of f evaluated at 0 is this guy right here, which is equal to 3 factorial. So we get 3 factorial on top, 3 factorial on bottom. So you can see those are going to cancel too. And so this trend is just going to keep on going. And so for the fourth derivative evaluated at 0, I get 4 factorial divided by 4 factorial, and then I have x to the fourth. And so hopefully you're like, oh gosh, these are all just going to cancel, gone, 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 gone. And so that's going to be equal to just a 1 plus an x squared plus an x cubed plus an x to the fourth. And so that's the fourth degree Taylor polynomial. And now the rest of these just solve themselves. Like if you want the 6th degree Taylor polynomial, what do you think it's going to be? There's clearly a pattern that is developed here. So we can just use that pattern. So that's going to be 1 plus x squared plus x cubed plus x to the fourth. And then you just keep on going to the 6th degree. So x to the fifth plus x to the sixth. So nice and simple. And then the 8th degree Taylor polynomial. So t sub 8 of x. Again, you just copy down everything. 1 plus x squared plus x cubed. And we're going to go all the way up to x to the 8th. So plus x to the fourth plus, hate those fours on this thing. So x to the fourth plus x to the fifth plus x to the sixth. 2 more guys, plus x to the 7, and then plus x to the 8. So once you establish the pattern, you can just use the pattern. You don't have to find those derivatives directly because the pattern's basically obvious once you make that table. All right, and that's how we find these Taylor polynomials. So again, let's look back at this formula here so you can just go see it. All right, so here's our formula again. And I guess here you can actually divide this by 1 factorial if you want. And over here, you can actually divide this by 0 factorial. Right, so 0 factorial is actually defined to be 1. Okay, so that's the Taylor polynomial. Now that's when it's centered at 0. So what happens if it's not centered at 0? So let's try one of those problems. So here's my example 2 here. I want to find the kth degree Taylor polynomial centered at 1 this time. So centered at 1, approximating the given function. So let's write down the 3rd degree Taylor polynomial, and we'll have it centered at 1. So what does that look like? So you have the original function, evaluate at 1, plus you take its derivative, f prime of 1, and then you can divide it by 1 factorial, but it's just the same thing. Then times x, plus the second derivative, ooh, you gotta be careful, not times x, it's centered at 1, so x minus 1, and then plus the second derivative, evaluated at 1, divided by 2 factorial, and then that's x minus 1 quantity squared, and then plus, we need one more because we need the 3rd degree, so we take the 3rd derivative of f, evaluated at 1, and then divided by 3 factorial, and then that's x minus 1 quantity cubed. So that's the 3rd degree Taylor polynomial. And understand, it's not that hard to remember because you're just using the function and its derivatives. And if you think about it, and I'll show you this, why this works here in a minute, but I kind of already alluded to it. If you think about it, I mean, that's just the idea. It's like at a point has lots of information on a function. It has the height of the function. It has the first derivative, the second derivative, the third derivative, the fourth derivative, the fifth derivative, all at that point. So if you can access that information, you should be able to build a polynomial out of it. And then that polynomial can be used to approximate the function. The only question really becomes is like, why do we have these weird factorials in here? You know, why do we have a factorial? In fact, you can put that factorial here. And if you wanted to, really a 0 factorial here. Why are these factorials in there? And so that'll be clear in a minute when I go over why this actually works. But let's finish off this problem. So to do this, I need to find the function and its derivatives at 1. So let's make a little table. All right, so the trick or the solution's always in the table. So here's my n. I'm going to find the nth derivative of the function. All right, so put a little parentheses around that n. And then I'm going to evaluate that not at 0, I'm going to evaluate it at 1 because this is the Taylor polynomial centered at 1. And so we'll do that for 0, and we'll do it for 1, and we'll do it for 2, we'll do it, and then we'll do it for 3, right, up to the third derivative. And so how about for 0? So remember, here's my function, ln of x, and so what's derivative ln of x? Oh, first you just write down ln of x, right? So for 0, it's just the original function ln of x. Then the first derivative is just 1 over x, or if you like, you can write that as x to the negative 1. For the next derivative, the power comes down, you take away 1, so you get negative x to the negative 2, which is really 1 over x squared. And then for the next derivative, right, so for the third derivative, the negative 2 is going to come down, you get positive 2, x to the negative 3, which is equal to 2 over x cubed. And so now we're going to plug in the number 1 here. So we get ln of 1, which is just equal to 0. We'll plug in 1 here, which is 1 over 1, which equals 1. And then here, I dropped off the negatives. That negative needs to stay there. I'll plug in 1 here, and I get negative 1 over 1 squared, which equals negative 1. And then finally, I'll plug in my 1 right there, which gives me what? 2 over 1 cubed, which of course is just equal to 2. So what is my third degree Taylor polynomial? So now I'm just going to plug in. So nice and easy. So what was f of 1? F of 1 was over here, ln of 1, which is equal to 0. So we put a 0 here. Plus, what's f prime of 1? Well, I come over here. F prime of 1 is just equal to 1. So I put a 1 right there times x minus 1. Plus, the second derivative of f evaluated at 1, just come over here. What is that equal to? So it's negative 1. So I'm going to write this as minus, and I'll plug in that negative 1. So it's minus 1 over 2 factorial x minus 1 quantity squared. And then finally, plus, what's the third derivative evaluated at 1? Well, that's a 2. And so I have 2 over 3 factorial x minus 1 quantity cubed. And so there's my third degree Taylor polynomial. So I'm going to clean this up a little bit. So this is going to be equal to, that just goes away. So we can just drop it off. And so I just get what? So I get an x minus 1. So write x minus 1 here. Plus 2 factorial is just 2. So it's 1/2 times x minus 1 quantity squared. And then plus, now 3 factorial, remember that what that is? That's 3 times 2 times 1. So that should be a 2 there times 1. And so notice these 2's are going to cancel. So I'm just going to get 1/3 times x minus 1 quantity cubed. And so that is the third degree Taylor polynomial centered at 1. And just for fun, so you guys can see what this actually does, let's graph the function ln of x and then this third degree Taylor polynomial to see what we get. So over here on my calculator, I'm going to graph ln of x, and then I'm going to graph here left parenthesis x minus 1 in parenthesis plus 1 divided by 2, and then left parenthesis x minus 1 in parenthesis quantity squared, and then plus 1 divided by 3 left parenthesis x minus 1 cubed. And let's just kind of compare and contrast these two graphs to see what they kind of look like. So we'll just do a standard window at first. So you can see like they're not actually exactly the same graph. So here's the standard. So there's my ln of x function right there. And over here comes that cubic function actually, because it's degree 3. And notice the two graphs are not the same, but if we zoom in towards 1, so on my calculator, I'm hit zoom and hit zoom in, and then I'm going to go over here to x equals 1 and then go up a little bit. And so then I'll just go x equals 1. This should work. And so x equals 1, I hit enter. So there's the ln function, just zooming in on x equals 1. And there's that cubic function again. And notice right here, they look almost the same. So I'm going to zoom in one more time, because as you get closer, the more these two functions basically look like each other. So I hit enter again. So there's 1 right there. So there's the ln of x. And then here comes that cubic function right there. And boom, right there and there. It looks just like that function. In fact, if we do one more zoom in, it's hard to even tell them apart, right? So there's the ln of x function, and then here comes that cubic function right there. So right there, they look basically the same, and they differ a little bit on the outside. So, and as the Taylor polynomial, you take a bigger and bigger degree, the better and better approximation we're going to get. And so that's the idea. So it's kind of like you can take all these functions and you can approximate them with polynomials. And then if you let that degree, that polynomial go to infinity, we get a power series. And so then we have a power series representation of that function. Sometimes a power series representation is the actual function, especially when the power series converges. All right, so let's do this last little bit right here just to try to explain where this formula actually comes from. So, you know, the big idea was what? So the big idea, let's do it right here. So the big idea is just, hey, if you give me this function f of x and you give me a point A, right? So you give me a point A here. At this point on the graph, there's some information. So what information do we have? We have the actual value, f of A. We have the derivative at A, f prime of A. And we have the second derivative right there at A, and then so on. So dot, dot, dot. So in third derivative, fourth derivative, fifth derivative, so on and so forth. So if we want to create a polynomial to fit this function, how should we make the polynomial? Well, at that point A, we should make sure the polynomial and the function have all the same values at that one point. So the actual height, the first derivative, the second derivative, third derivative, fourth derivative, fifth derivative, and so on. If we can do that, then maybe that polynomial will be a good approximation to that function. So what we're going to do is we're going to center this at 0 because it's easy to look at, and we're just going to take a third degree polynomial. So this is just a heuristic proof of where this formula basically comes from. And so if we have a polynomial, a third degree polynomial here, where a, b, c, and d are just constants, and it were to behave like f of x at 0, then we expect a polynomial when you plug in 0 that you get what? So you should get f of 0. And at p prime is 0, you should get f prime of 0. And if p double prime is 0, you should get f double prime is 0. So this is how we want to make our polynomial, basically. In the third derivative, we'll want to make sure that the third derivative of f evaluated at 0 and the third derivative of our polynomial value 0 are exactly the same. So we're going to create a polynomial that has these four properties, right? So it's a third degree polynomial, and the height of the function and the polynomial are the same. The first derivative of the function of the polynomial is the same. The second derivative of the polynomial and the function are the same. And the third derivative of the polynomial and the function are the same at 0, right? So at a single point. So let's see what that forces our A, B, C, and D to actually be. And so here, if you take your polynomial and you plug in 0, you're just going to get out D, because all these terms, right, these are going to be 0, 0, 0, and so you're just going to get back your D. And so you want f of 0 to be equal to D. So what's D equal to? D is just equal to f of 0. Now take a derivative of your polynomial, right? So it's just basically what? The power comes down, you get 3x squared. The 2 comes down, 2bx plus c, derivative d is 0. Now plug in 0 again. So you put a 0 here, you put a 0 there. Those terms go away, and you just get c. So c is equal to the first derivative of f evaluated at 0. So that's what c should be. And then we do a derivative again. So now the 2 comes down, and we get 3 times 2 times a, and times x plus, and now here, you have that x, so you just get 2b, and now you plug in 0 again, so put a 0 right here, and you just get 2b. And so then what's b equal to? We'll divide both sides out by 2, so you're going to get f double prime of 0 divided by 2. And then finally, for the third derivative right here, maybe I should erase these guys so you can kind of see how the derivatives are working, right? So for the third derivative, you take a derivative of this guy, and so you get 3 times 2 times a, and then plus 0, because this is just a constant. And so when you plug in 0, you just get 3 times 2 times a. And so what's the a equal to? Well, it's just the third derivative evaluated at 0 of this function f, and then divided by 3 times 2. And so now, I'm going to make this a little smaller here. So now, what can we do? So therefore, what's our p of x? Well, we know our D is f of 0, so I'm just write this backwards. So our D is f of 0. Our C is f prime of 0, so we'll put f prime as 0. And then our B is f double prime of 0 divided by 2, which you can write as 2 factorial if you want. So f double prime of 0, so f double prime of 0 divided by 2 factorial. And then guess what our A is? Well, our A is just this guy, and we got 3 times 2 is 3 factorial. So this is the third derivative of f evaluated at 0 divided by 3 factorial, which is just the third degree Taylor polynomial centered at f of x. So that's where this formula up here basically comes from. It's just this idea like, hey, let's create a polynomial that has this property that the polynomial evaluated at a is equal to f of a. The first derivative of the polynomial evaluated at a is equal to f prime of a. And the second derivative of the polynomial evaluated at a is f double prime of a, and so on and so forth. And so if you try to create a polynomial like that, you get these Taylor polynomials. And so the point of this is to be like, hey, this doesn't come out of nowhere. This is actually, if you think about it, a very obvious idea. You got a function, you know its height, you know its derivative, its second derivative, third derivative, all at this one point, and just one point. You just have that information. We can use that information to create a polynomial that has that same information at that point, and then it's like magic. Oftentimes, that polynomial will give you a really good approximation for that function around that point. And as you let that degree go to infinity, guys, that's where you get the power in the power series, right? So the next lecture, we'll talk about how we find these power series, but it's just like I find in a Taylor polynomial, you just let n go to infinity, right? So it's like it's a power series instead of a polynomial. All right, that's all I have for you guys today.